Welcome students. Today we will discuss about the intermolecular forces. Intermolecular forces are the weak interactions present between two separate molecular species. They are different from the chemical bonds which are present within the molecule. Chemical bonds like ionic bond or covalent bond or metallic bond bind the atoms within the molecule, whereas intermolecular forces bind the various molecular species which are separate from each other. Intermolecular forces are weaker in comparison to the chemical bonds. Let us take an example. Suppose you have two separate HCl molecules. Then these are chemical bonds which are binding hydrogen with the chlorine atom. They are present within the molecule. But in between these molecular species, some interactions also work. They are weaker in comparison to the chemical bond present in the HCl molecule. And these are intermolecular forces. Intermolecular forces are of many types. In the next slide, we'll discuss various types of the intermolecular forces. The first type of intermolecular force is dispersion force. Dispersion forces are also called as London forces. This kind of intermolecular forces are very weak intermolecular forces and found everywhere. Whether your molecular species is polar or non-polar, these forces will definitely work. But in between the non-polar species, these are the only forces found. Let us take an example of the atom. An atom is non-polar in nature. Why? Because it has symmetrically distributed electron cloud around the nucleus. But you know that electrons are moving, and that's why electron may go by chance towards one side of the nucleus and make the atom polar in nature, as shown in this diagram. The end at which nucleus is present become partially positive, and another end where electron cloud is situated that become partially negative, and your atom will now change to instantaneous dipole. Why I am saying it instantaneous dipole? Because it is formed for a very short period of time. After some time this will again change to its original form. But meanwhile it will induce its effect into another atom. It will repel to the electron cloud of another atom, and as a result another atom will also change to instantaneous dipole or temporary dipole. Now these two dipoles attract to each other. Positive end of one of the dipole and negative end of the another dipole attract to each other with a weak interaction. This interaction is nothing but a dispersion force. So this is the origin of dispersion force. How the dispersion force come into the existence? First of all, your non-polar atom change to instantaneous dipole. Then this will induce another instantaneous dipole in the nearby atom, and then these two instantaneous dipole attract to each other through a weak interaction, and that is dispersion force. You can understand it on the basis of helium gas. I have shown here two atoms of the helium which are non-polar initially because they have symmetrically distributed electron cloud around their nucleus, but for a short span of time one of the atom changed to instantaneous dipole because of the movement of its electron at one side of the atom. So positive and negative ends be formed. Now this atom will induce another instantaneous dipole in nearby atom, and as a result another atom will also be changed to instantaneous dipole, and this is called as induced instantaneous dipole. Now instantaneous dipole and induced instantaneous dipole attract to each other through a weak electrostatic attraction, and that is dispersion force. After some time both of these atoms will change into their original form, so this effect will be lost. But always a sample of helium gas contain few pairs of instantaneous dipole and induced instantaneous dipole, and that's why there will be some weak attractive forces always present between the atoms of helium, and such forces are called as dispersion forces. Not only in the atoms, they are found in the molecules also. For example, I have shown here two H2 molecules. Initially they have equally distributed electron cloud, so they are non-polar, but after some time in one of the molecule instantaneous dipole is created because of the movement of electron at one side of the molecule. Now this will create or induce another instant dipole in the nearby molecule, and now these two, instantaneous dipole and induced instant dipole, interact to each other, and such interaction is dispersion force. Always the sample of hydrogen gas contain few pairs of such instantaneous and induced instantaneous dipoles, and therefore this kind of interaction is very weak because only few pairs are found in a sample of molecular species. Now another thing about the dispersion forces. Dispersion forces depend upon the size and surface area of the molecular species. More the molecular size, more the surface area, more the strength of the dispersion force. In this table, I have shown how the dispersion forces are increased as the surface area increases. Let us take the example of zero group or noble gas group in the periodic table. The gases are helium, neon, argon, krypton, xenon, and radon. As you go down this group, the molecular size will increase. When not the molecular size but the atomic size will increase. As the atomic size increases, the surface area of the atom will be increased, and because of that, magnitude of the dispersion force will be increased. And when the dispersion forces among the atoms increases, the boiling point will also be increased. You can see from the table, helium being smallest in size has least surface area of the atom, and therefore weakest intermolecular forces, so the boiling point is least. Whereas see radon, that is having biggest atomic size, so biggest surface area, and therefore the maximum dispersion forces are found, and therefore the maximum boiling point of this species. So in this way, more the size, more the surface area, more the strength of dispersion forces, and when there is more the strength of dispersion, more the boiling point. So one thing you may note here, more the strength of intermolecular force, more will be the boiling point or melting point of the species. See another example. In this example, I have shown straight chain alkanes. The first one is N-pentene, second one is N-hexane, then N-heptane, then N-octane, and then N-nonane. These are straight chain alkanes in the increasing order of their molecular mass and therefore the molecular size. As you go towards the higher members in the alkane series, not only the molecular mass increases, the molecular size will increase, the surface area will increase, and that's why the dispersion forces acted among their molecules will be increased, and so the boiling point will increase. You can see in this graph the boiling point is increasing. Okay, the N-pentane, which is smallest in size, having smallest surface area, having least dispersion forces, and therefore it is having least boiling point, whereas this N-nonane is biggest in size, it is having biggest surface area, and therefore it is having strongest dispersion forces, so its boiling point is maximum. One more example I am going to take. I have taken three isomeric alkanes. One is normal pentane, which is having unbranched 5 carbon chain. Second is 2-methylbutane, which is having a branch, and third one is 2,2-dimethylpropane, which is having 2 branch. But the molecular formula for all these species is same, and that is C5H12. So molecular formula is same, only the number of branching is changing. N-pentane is having unbranched atomic chain of carbon, whereas 2-methylbutane is having one branch, and 2,2-dimethylpropane is having two branch. As the number of branches in the isomeric alkanes increases, the molecule becomes spheroidal. Its sphericality will increase. You can see from the diagrams. It is least spherical, it is more spherical, and it is the most spherical molecule. So as the number of branches increases among the isomeric alkanes, the sphericality of the molecule will increase, and as a result the surface area will be reduced. When surface area reduces, the dispersion forces will also be reduced, and therefore the boiling point of the molecular species should decrease. You can see from the boiling points given here. Okay, so this is also the example how the dispersion forces strength depend upon the surface area. So more the branches among the isomeric alkanes, more the sphericality, lesser the surface area, lesser the dispersion forces, and lesser the boiling points. So this is all about the dispersion forces. So I want to revise here. Dispersion forces are found everywhere among the non-polar molecular species. They are the only intermolecular forces. Okay, the strength of such forces will be directly proportional to the surface area of the molecular species. More the surface area of the species, more the dispersion forces. Now the second type of intermolecular force, that is dipole-dipole interaction. As this name indicate, this kind of interaction will work between two polar molecules. I have shown here two HCl molecule. H and Cl have different electronegativities. Cl is more electronegative than the hydrogen, so it will pull the shared pair of electron towards it, and as a result hydrogen become partially positive and chlorine become partially negative. So this kind of molecule is a permanent dipole molecule. Another HCl molecule is also a permanent dipole. Now the negative end of one HCl molecule will attract to the positive end of another HCl molecule, and this kind of interaction is called as dipole-dipole interaction. Means positive end of one dipole attract to the negative end of another dipole. So that type of interaction is called as dipole-dipole interaction. It is comparatively stronger than the dispersion force, because in case of dispersion forces, dipoles are first created and then they interact, whereas in dipole-dipole interaction there are already dipoles present. There are permanent dipoles which attract to each other, and therefore the interaction will be comparatively stronger. Okay, this kind of interactions become stronger as the electronegativity difference between the bonded atom increases, because as the electronegativity difference between the bonded atom increases, the polarity of the chemical bond will be increased, the dipole moment of the molecule will increase, and more the dipole moment of the molecule, more the dipole-dipole interaction. ठीक है, तो अगर मैं कंपेयर करूं HCl और HS बॉन्ड के डायपोल मोमेंट्स को, ओके, तो HCl molecule have stronger dipole-dipole interaction, and HS bonds have weaker dipole-dipole interactions. Why? Because here the electronegative difference is comparatively high. HS bonds are found in H2S. So in comparison to H2S, HCl have stronger dipole-dipole interactions, whereas H2S has weaker dipole-dipole interaction. The reason is in between H and Cl there is high electronegativity difference, so there is high polarity of the HCl molecule, so there is high dipole moment of the HCl molecule, and therefore there will be stronger dipole-dipole interaction between the HCl molecule, whereas in H2S the HS bonds are less polar because sulfur is less electronegative than the chlorine, and therefore the electronegative difference between the HS is less, and therefore the dipole moment of the molecule will be less, and so the dipole-dipole interactions will also be weaker between two H2S molecules. The another type of intermolecular force is dipole-induced dipole interaction. As the name indicates, this is interaction active between a polar molecule and a non-polar molecular species. Dipole-dipole interaction works between two polar species, whereas dipole-induced dipole interaction will work between a polar and a non-polar species. For example, interaction between oxygen molecule and water molecule. Oxygen, when taken in the isolated form, is non-polar. Why? Because in oxygen molecule there are two oxygen atoms which are having same electronegativity, so they have equal distribution or symmetrical distribution of electron cloud, and therefore this oxygen molecule is non-polar in nature. But water is not non-polar, it is polar in nature. Why? Because it is a V-shaped molecule having two OH bonds. Each OH bond is polar in nature because oxygen is more electronegative than the hydrogen, and due to the V shape the two OH bonds cannot cancel their dipole moments, and therefore H2O molecule overall is having a dipole moment, and so it is a permanent dipole or a polar molecule. When O2 molecule interact with the water molecule, then dipole induced dipole interaction will develop. How they develop? The negative end of the water will induce a dipole momentum in the non-polar oxygen molecule. The negative end of the water will repel to the electrons of the oxygen molecule, so electron will go at the far end from where the water is interacting, and as a result your oxygen molecule turn into an induced dipole, whereas water molecule is already having a permanent dipole. Now the positive end of the induced dipole and the negative end of the permanent dipole interact to each other through a weak electrostatic attraction, that is dipole induced dipole interaction. This kind of interaction is weaker in comparison to the dipole-dipole interaction. Why? Because here only one molecular species is permanent dipole or polar, and second is induced dipole. Therefore, the interaction between a polar and non-polar species will be weaker in comparison to the dipole-dipole interaction. Another kind of intermolecular forces are hydrogen bonds. Hydrogen bonds are special case of dipole-dipole interaction. They are very strong in comparison to normal dipole-dipole interactions. They are formed between those species which have hydrogen attached to a highly electronegative atom which are small in size. In periodic table, only three such atoms like fluorine or oxygen or nitrogen. When hydrogen is attached to fluorine or oxygen or nitrogen, then only hydrogen bonding will be possible. Let us take the example of water molecule. In water molecule, oxygen being electronegative is partially negative charge, and hydrogen being electropositive is having partial positive charge. Now hydrogen of one of the molecule will attract to the oxygen of another molecule through weak electrostatic attraction, that is hydrogen bond. So this is as like dipole-dipole interaction, but it is stronger. See in this diagram, here central water molecule is making three hydrogen bonds with three separate water molecules. In each of the hydrogen bond, hydrogen of the one molecule is attracting to the electronegative oxygen atom of the another molecule. Hydrogen bonding is also possible in ammonia molecule, because in ammonia hydrogen is attached with nitrogen, that is also a highly electronegative atom, so the NH bond is also highly polar, and therefore hydrogen attached with nitrogen is able to make hydrogen bonds. So you can see here hydrogen of one molecule is interacting nitrogen of another molecule, and this type of intermolecular force is hydrogen bond. In HF molecule also you will find hydrogen bonds. Fluorine and hydrogen of two separate molecules interact to each other through hydrogen bonds. Hydrogen is partially positively charged and fluorine is partially negatively charged. The partially positively charged hydrogen of one molecule interact with the partially negative charge fluorine of another molecule, and that interaction is hydrogen bond. Now I want to compare here boiling point of hydrides. I will take the example of group 14 elements. Here it is mentioned group 4. As per the Mendeleev periodic table, group 4, and as per the modern periodic table it is group 14. So if you compare the boiling point of hydrides of group 14, how will you explain? The first member is carbon, its hydride is methane. Second is silicon, its hydride is SiH4. Third is GeH4. Fourth is PbH4. Okay, so as you go down in the group 14, you will find these hydrides CH4, SiH4, GeH4, PbH4. The boiling point will increase in this order. CH4 is having least boiling point and PbH4 is having maximum boiling point. How will you explain the order of boiling point? You will explain on the basis of intermolecular forces. What kind of intermolecular forces are found here? Methane molecule will interact together through dispersion force. Why? Because methane is a non-polar molecule. It is a tetrahedral molecule, and all CH bond neutralize their dipole moments because of regular geometry. So methane molecule is a non-polar molecule. Similarly, SH4, GH4, PbH4 all are non-polar molecules. CH4 molecule, as they are non-polar, they will interact together through dispersion force, and the strength of dispersion forces depend upon the surface area. So as you move from CH4 to PbH4, the central atom size will increase, so the molecular size will increase, so surface area of the molecule will increase, as shown here by the circles. I have shown the size of the molecule. As the central atom, that is carbon, silicon, germanium, lead, as the central atom size increases in the hydrides, the overall molecular size will increase, so the surface area of the molecule will increase, so the dispersion force strength will be increased, and therefore the boiling point will increase. So least boiling point is for the methane and highest for the PbH4. Now come to the group 15. This yellow curve is for the group 14 hydrides, and this is for this red curve is for the group 15 hydrides. Now first member is NH3, second is PH3, third is ASH3, and fourth is SBH3. PH3 to SBH3 continuously boiling point is increasing, but NH3 to PH3 it is decreasing. Why? So PH3 to SBH3 you will explain on the basis of same fact. The central atom is increasing in size, therefore the overall molecular size will increase, and that's why the surface area of the molecule will increase, so dispersion forces acted among the molecule will increase, and so the boiling point will increase. So PH3 to ASH3 and then ASH3 to SBH3, boiling point will increase because of the increase in the strength of dispersion forces acted between the molecules. Lekin NH3 is the first member, it should have least boiling point. Why it is having higher boiling point in comparison to PH3? The reason is in NH3 hydrogen bonding is found. In NH3 hydrogen is bonded with nitrogen, which is highly electronegative and small in size. So NH3 molecules have hydrogen bonds association between them, which is stronger kind of intermolecular force, and therefore the boiling point of NH3 is exceptionally higher than the PH3. In PH3 hydrogen bonding is not found because hydrogen is bonded with phosphorus, which is not so electronegative and it is bigger also. That's why in PH3 there were only dipole-dipole interaction will work, which are weaker in comparison to the NH3 hydrogen bonds, and therefore the PH3 boiling point will be lesser than the ammonia. Okay, While discussing the order of boiling point of PS3, ASS3 and SBS3, we don't compare their dipole-dipole interactions because dipole-dipole interactions don't vary so much. But the dispersion force is the dominant factor that vary comparatively more, and therefore it will decide the boiling point. PS3 to SBS3, dispersion forces become stronger and stronger, so boiling point increases. Okay, but here dipole-dipole interaction are also working. Okay, and in NS3 dispersion forces no doubt are less, but hydrogen bonds are present which are stronger, very stronger, and therefore the boiling point of ammonia molecule will be very high as compared to the PS3. The same trend is found in group 17 and 16 also. This is graph for group 14, this is for 15, this is for 16, this is for 17. Okay, so you can see that the same trend is found in group 15, 16 and 17 hydrides. The first member of every group among the group 15, 16 and 17 is having higher boiling point. It is because of hydrogen bond association. Okay, second member cannot have hydrogen bonds. Why? Because the size of the central atom will be increased, so it cannot make hydrogen bond. Electronegativity decreases and size increases. Okay, there will be only dipole-dipole interaction. Okay, and after that when you move towards more higher hydride, then the dispersion forces become stronger and stronger. Because of that, boiling point will increase. Okay, so the boiling point trend will be like that. From first member to second member decreases, and then second member to higher member it will be increased, and that is not found in the group 14 because in group 14 we will take only the dispersion forces in our account. Hydrogen bond association is not found because the first member of the 14 group is carbon. Carbon is not electronegative atom, so hydrogen attached with the carbon cannot make the hydrogen bond. Okay, now hydrogen bonds are two types: intermolecular hydrogen bonds and intramolecular hydrogen bonds. The hydrogen bonds which we have discussed here, they all are intermolecular forces. It means hydrogen bonds found among the water molecules, among the ammonia molecules, among the HF molecules. These all are intermolecular forces because they are the forces active between two separate molecular species. But if hydrogen bond found within the molecule, and that is called as intramolecular hydrogen bonding. You can see intramolecular hydrogen bonding in the case of orthohydroxybenzaldehyde and orthonitrophenol. You can see here, this is the intramolecular hydrogen bonding. Hydrogen attached to oxygen is interacting oxygen of same molecule. So hydrogen bonding is present within the molecule. So this kind of hydrogen bonding is intermolecular hydrogen bonding. The same is in the orthonitrophenol. This is the intermolecular hydrogen bonding. The result of or the effect of intramolecular hydrogen bonding is just opposite to intermolecular hydrogen bonding. Intermolecular hydrogen bonding increase the boiling point, whereas intramolecular hydrogen bonding decrease the boiling point. If you compare boiling point of this para nitrophenol, then the boiling point of this molecule is comparatively higher. Why? Because here the NO2 group is far from the OH group, so the hydrogen bonded to oxygen is not able to make hydrogen bond with the NO2 group of this molecule. So intramolecular hydrogen bonding is not possible, and this molecule will make intermolecular hydrogen bonding. Means hydrogen of one molecule will interact with the oxygen of another molecule, and so intermolecular hydrogen bonding will be possible, and that will increase its boiling point. So para-nitrophenol is having high boiling point, whereas orthonitrophenol means this one here, due to the intermolecular hydrogen bonding, the boiling point will be lesser. Now another kind of intermolecular force is ion-dipole interaction or ion-dipole forces. As this name indicate, here one of the species ion, maybe cation, maybe anion, and another is polar species. In the first diagram I have shown negatively ion negatively charged ion is interacting with the polar species, and the second cationic species is interacting with the polar species. When you dissolve sodium chloride in water, first of all it ionizes to give Na plus and Cl minus ion. Cl minus ion and Na plus ion both will interact with the water molecule, and they will interact through ion-dipole interaction. Each chloride ion will interact with so many water molecules as shown in this diagram. Okay, water molecule is a permanent dipole. It is polar in nature. Its hydrogen are positively charged, whereas chloride is having negative charge, so they attract to each other. So in this way, ion-dipole interaction will work between chloride and water molecules, and so many water molecules surround the chloride ion. Similarly, the cation of NaCl will also interact with the water molecule, because oxygen of water molecule is negatively charged and it is attracted by the cation. So many of the water molecule attract to Na plus ion through ion-dipole interaction. The difference between the two cases is that in the case of negatively charged ion, hydrogen is pointed towards the negative ion, whereas in case of positively charged ion, the oxygen atom of the water is pointed towards the cation. But both forces are ion-dipole interactions. So ion-dipole interactions are the interaction between a particular ion, maybe a cation, maybe an ion, and a polar species. The dissolution of water, dissolution of NaCl in water is due to these ion-dipole interactions. The hydration of ion is nothing but it is due to the ion-dipole interaction. Surrounding of an ion by the water molecule is termed as hydration, and hydration results due to ion-dipole interaction formation. Next type of intermolecular force is ion-induced dipole interaction. As this name indicates, here one of the species is ion, maybe cation, maybe an ion, and another species is a non-polar species. For example, Fe plus 2 when interact to the oxygen molecule. Fe plus 2 is cation, and oxygen molecule is a non-polar species, because here the oxygen atoms have same electronegativity and symmetrical distribution of electron cloud. But when Fe plus 2 interact, it will attract to the electron cloud of O2 molecule. As a result, the oxygen which is near to Fe2 plus become negatively charged, and another end which is far from the Fe plus 2 become positively charged. In diagram this is shown wrong. Okay, why? Because Fe plus 2 is attracting electron pair towards it, and therefore the oxygen which is near to Fe2 plus become partial negative, and another atom become partial positive. Okay, now the oppositely charged end of the oxygen molecule will interact to the ion, and therefore ion-dipole interactions are formed. This kind of interactions are weaker in comparison to the ion-dipole interaction. Why? Because in the ion-dipole interactions, ion is interacting with a permanent dipole, whereas in ion-dipole interaction, ion is interacting with a non-polar species. So the interaction is here weaker. Ion-induced dipole interaction is a weaker interaction. Okay, if anion will interact, the ends will be just opposite. The end near to the anion will be positive, and the end which is far from the anion will be negative. Okay. This slide is showing you dipole-induced dipole interaction. One more example I have taken here. Dipole-induced dipole interaction is also called as Dipole forces. SCl is a permanent dipole, and Ar, which is non-polar atom. When Ar atom means organ atom approaches to SCl, then dipole-induced dipole interaction will work. The positive end of the SCl will attract to the electron pair of the electron cloud of the AR, and as a result the end near to H become partial negative and the end far from the hydrogen become partial positive, and now induced dipole will be formed, and this induced dipole interact with the permanent dipole, and this kind of interaction is called as dipole induced dipole interaction, which is also called as Debye force. Now summary of all the intermolecular forces. Here I will show you what should be the strength of the intermolecular force, means we will arrange various kind of intermolecular forces according to their strength. तो आप देखिए बॉटम मोस्ट पोजिशन पर प्रेजेंट है डिस्पर्शन फोर्स और लंदन फोर्स. दे आर द वीकेस्ट टाइप ऑफ intermolecular forces. Then dipole induced dipole, then ion dipole, ion induced dipole, then dipole dipole, then hydrogen bond, and the strongest are ion dipole. So weakest are dispersion forces, strongest are ion dipole interactions. Okay, hydrogen bonds are in between dipole dipole and ion dipole interactions. Okay, whereas ion induced dipole interactions are in between dipole dipole and dipole induced dipole interactions. Okay, so from this table you can easily understand the strength of various kind of intermolecular forces. So this is all about the intermolecular forces.